Hi everyone, I'm Huaxin, a PhD student from the Penn State University. Today I'm going to introduce our work about improving fairness in speaker verification via group-adapted fusion network. This work is collaborating with Amazon Alexa scientists Yu Guangyang, Guo Lisun, Ryan Lehman, Jung Christine Han, Yasha Drapo, and Andrea Stocco. As we know, the performance of speaker verification systems has dramatically improved due to both deep learning algorithms and large-scale datasets. Well, the state-of-the-art speaker verification models typically have two stages, including the deep embedding encoders to be the front end, which compute speaker embeddings from speech audio, and the scoring function as a backend, which generates similarity score between two embeddings. In these speaker verification systems, we need to train the front-end deep embedding encoders with commonly used classification or metric learning objectives. For example, the metric learning objectives aim to optimize the speaker embeddings to have smaller distance between the same speakers and, meanwhile, larger distance with different speakers, so that the backend similarity score can better differentiate speakers. However, this learning process can potentially lead to model unfairness across groups. It's mainly because during the training, models are trained to minimize average loss over the full datasets, which can cause voice characteristics of underrepresentative groups to be largely ignored. Besides, for evaluation, the common performance metrics such as equal error rate typically measure overall performance across groups, which does not reflect performance over different subgroups. Therefore, in this work, our goal is to rigorously analyze model unfairness in speaker verification systems and offer a generalizable solution to alleviate model unfairness. We conclude our contributions from three aspects. First, we originally crafted training and evaluation datasets and evaluation metrics to rigorously evaluate and analyze model fairness performance. Besides, we provide direct evidence showing that group imbalanced training dataset can lead to model unfairness to underrepresentative groups. Further, we propose a flexible modular model based on group embedding adaptation and score fusion to alleviate model unfairness. We start with introducing our proposed method. The core idea here is to improve the front-end encoders with group-wise adaptation encoders to capture the fine voice characteristics of each group, and then use score fusion strategy for backend to aggregate scores from all groups' embeddings. We therefore name our method as Group-Adapted Fusion Network. To be more specific, in the front-end stage, we train a base encoder with group mixed data. Then we fine-tune this base encoder with group-specific data to get the group-wise adaptation encoders. Therefore, we can extract base and group-adapted embeddings. In the backend stage, given the well-trained adaptation encoders, we compute all similarity scores and aggregate them with the score fusion model to get the final score. We train this neural network score fusion model using the binary cross-entropy loss. To rigorously train and evaluate the model fairness, we crafted the datasets and metrics. To examine the effects of imbalanced group size in training set, we construct the Voxelab2 GRC named Gender Ratio Controlled Training Sets, where we control the total speakers to be all the same as 2,500, then only modify the ratio of female and male. We further sample pairs from this dataset to train the backend model. For the test set, we create Voxelab1 fairness dataset, where we control the size of each gender trial types so that we can use it to strictly evaluate the model fairness. In terms of the evaluation metrics, our metrics are based on equal error rate, which is one of the most common metrics to evaluate speaker verification models. Then, we measure model fairness with 3 metrics here. The group-wise EER to monitor the female and male-specific performance. We use overall EER to monitor performance across all groups, and use disparity score to check the model performance gap between groups. All metrics are lower, the better. So, given these settings, the first research question we want to ask is, does imbalanced group size in training dataset cause model unfairness? Well, the short answer is yes. In detail, we train the 2 baseline models on the Voxelab2 GRC training sets, where QRN is the quarter-channel ResNet and HRN means half-channel ResNet. From the figure, we find that when training with imbalanced group ratio datasets like 9:1, the dominant group always achieves better group-wise EER than the underrepresentative group. Besides, increasing the dominance of one gender group leads to increasing DS score and overall EER. This indicates the increase of model unfairness and error rate. Therefore, we conclude that imbalanced group ratios in training sets can lead to model unfairness towards underrepresentative groups. Furthermore, we also ask, can our proposed GFN model improve model fairness? Here we design all GFN's encoders as QRN model, and we find that GFN achieves better group-wise and overall EER than baselines, regardless of gender group imbalances. Besides, it also reduced the disparity score in most gender ratios. We thus conclude that GFN model can improve model fairness and performance reflected by group-wise EER, overall EER, and DS scores. Next, we visualize the embeddings from baseline and GFN model with Tisney project method, where we find that genders tend to aggregate in different embedding space regions, which supports our design of group embedding adaptation. Besides, we find GFN tends to aggregate higher quality embeddings than baseline, showing more compact for same speakers and separate for different speakers. Last, we conducted ablation studies to verify the necessity of our GFN model design, where we compare GFN with 4 alternative methods and 2 baselines. We find that the GFN achieves the best performance among all methods. Please see our paper for more details of the listed methods. So, to summarize, in this work, we use evaluation metrics and datasets with defined group ratios to analyze model fairness performance. Further, we provide the direct evidence that imbalanced group presence can lead to model unfairness to different subgroups, specialized in gender group settings. Besides, we propose group adaptation fusion network based on group embedding adaptation and score fusion to counteract model unfairness. Finally, we demonstrate that GFN reduces group disparity for imbalanced training scenarios while reducing overall speaker verification EER. Our crafted Voxelab 2 GRC and Voxelab 1 fairness datasets are open sourced at GitHub. Please feel free to check out. Last but not least, I want to thank all the scientists from Amazon Alexa who provided valuable discussion and feedback on our work. Also, I appreciate my Amazon intern advisors and the audience of this video. Thank you for listening.